All right, thank you very much. Is the mic working? Good. So these will be some introductory lectures to supersymmetry. Before diving in, let me just tell you that there are, of course, many different reasons that one could study supersymmetry. It's a fundamental ingredient in string theory. It might be a real symmetry of nature, deep down. But more important for the theme of these lectures, and I think for this school, is that supersymmetry is a very powerful tool that can help you learn new things about quantum field theories. So you can make it as an assumption, study quantum field theories or quantum mechanics problems that happen to have supersymmetry, and you can learn a lot about general field theory this way. So that will be sort of the spirit of these lectures. And I'll assume that you don't know much about supersymmetry, unlike the many of the other lectures. Supersymmetry will build throughout all of TASI, so there'll be one Susie speaker each week, so it's a bit cumulative. So hopefully there'll be some interesting points for those of you who have seen it before. All right, so let's get started. Today we're going to do supersymmetric quantum mechanics. Okay, so what we'll do is we will introduce the supersymmetry algebra in quantum mechanics. So we'll start in 0 + 1 dimensions. That means we can divorce all the complications of spin from the study of supersymmetry. And we'll see the general algebra and its features, and then we'll also see how those features play out in a very nice toy model. Okay, so what is the algebra? So the algebra is the following. So we have a Hamiltonian H, and we have some generators Qi. I will go from 1 to n, and n is called the number of supersymmetries. And these generators are symmetries of our problem, meaning that they commute with the Hamiltonian H. Okay, so far that would have been standard for any symmetry. The non-trivial thing about the supersymmetry algebra is that we'll postulate another relation. The anti-commutator of two supercharges will be equal to the Hamiltonian itself, up to some factor of 2. And here I'm working with Hermitian supercharges. So the adjoint of every supercharge is itself. So this equation in particular means that Qi squared is the Hamiltonian. So supersymmetry and supercharges can be viewed as a kind of square root of the Hamiltonian, and that will turn out to be extremely powerful. Okay, so this is not quite all there is to the algebra. There is another important object in the theory that we should introduce. So there is a Z2 symmetry. Every supersymmetric theory has a Z2 symmetry, which is sometimes called -1 to the f, where f is the fermion number. But fermion number f makes sense only mod 2. So we can assign this, this charge to be either even or odd, plus or minus 1. Now, when you have a symmetry like that, we can decompose the entire Hilbert space of our theory into states that are even under Z2 and states that are odd under Z2. So we can take our Hilbert space and we can write it as a direct sum. So here B will be called the Bosonic States. So if you have a state in HB, then -1 to the f on this thing just gives you back B. And if you have a state in the fermionic part, it's the opposite. And of course, we can grade the operators in our theory by this Z2 symmetry as well. So we say that an operator is bosonic. So if -1 to the f gives you back O, and an operator is fermionic if instead you get a minus sign. Now, okay, part of the definition of the supersymmetry algebra is to tell us that Q is fermionic. That means Q maps from HB to HF, so it changes the eigenvalue, and vice versa, HF to HB, the Hamiltonian is bosonic. And in fact, I already told you that because I told you that Z2 is a symmetry of our problem, this minus 1 to the f. So that means that it commutes with the Hamiltonian, which is what happens for any bosonic operator. Okay, so this is the definition of the algebra and its basic properties. And now I'm going to give you an example system that has this symmetry. Are there any questions about this basic definition? Okay, so we're going to consider the main example of this in this lecture will be a particle with spin. So we'll have a wave function phi, which is going to have two components, phi plus of x and phi minus of x. So it's a particle moving in one dimension. There'll be only one coordinate x. What is the Hamiltonian? We have a standard kinetic term. Okay, so what have I done here? So this particle with spin depends on a new function. This problem that I'm talking about depends on a new function, w of x. Oh, excuse me, thank you. Yep. This particle with spin depends on a new function, w of x, which is called the superpotential. So the superpotential is any function you like. And once you pick a superpotential, I'll define for you a Hamiltonian by this formula. So what's going on here? So first of all, we took the derivative of the superpotential and we squared it. So this is an ordinary kind of potential energy term. And it's positive definite because we've squared w prime. Now, yeah, w is real, yes. Yes, here in this problem, w is real. We're considering everything inside is real. So what's the next term? This can be viewed as a kind of magnetic field term. So why is it a magnetic field? It's because it couples to the spin. We've got sigma 3 here. And okay, so both these terms on their own look totally benign. We're used to considering problems with potentials, and in fact there's nothing special about this potential. We've just made it positive. And we're used to considering problems with magnetic fields. The special thing is that there's a relation between the potential and the magnetic field. So that's what's going to make this model interesting and give it the supersymmetry. And that's going to be a general point throughout, is that supersymmetric theories will look just like ordinary theories in that they have sort of ordinary looking interactions like potentials and couplings to spin, but there'll be special relations between those interactions that will give it the extra symmetry. Okay. So this is a Hamiltonian. It depends on a real function, w of x, and given that real function, you make this problem. Let's define the symmetries. Let's see the supercharges. So I'm going to define Q1 and Q2. First I'll just pull it out of a hat, and later we'll see eventually how to get these from some more general reasoning. So here's Q1, and this model will in fact have n equals 2 supersymmetry, so I'll be able to define both Q1 and Q2. Okay, so these are the candidate supercharges. So this is supposed to realize n equals 2 supersymmetry. In order to prove that it realizes supersymmetry, I should compute now all these commutators. Okay, I won't do all of it, but maybe we'll check one relation. So let's check, for instance, that Q1 squares to the Hamiltonian. Okay, so what kind of terms are we going to get when we square Q1? So we'll get this squared, and cross terms. And the interesting part is that since this is a momentum operator, this momentum operator can act on the superpotential. So from one term, we get p squared over 2m sigma 1 squared. From another term, we get m over 2 sigma 2 squared w prime squared. Now the cross terms. So we get 1/2. I dropped an h bar. No, I didn't drop an h bar. You can tell I'm not used to thinking about h bars. Okay, so sigma 1 p, I guess this is a minus sign, sigma 2 w prime, and then minus 1/2 sigma 2 w prime sigma 1 p. Okay, so sigma 1 squared and sigma 2 squared are both 1. It's a basic property of the Pauli matrices. So we got the kinetic term, and now we get the potential term. Now here, p is minus I h bar d by dx. So we can try and move p to the other side here, and we'll pick up an additional term when the derivative hits w prime. So we'll get minus 1/2 sigma 1 sigma 2 w prime prime, and we get a I over h bar. Good. Now we've got the other term minus 1/2 sigma 1 sigma 2 w prime p, and then we get minus 1/2 sigma 2 sigma 1 w prime p. Good. So these are Pauli matrices with different indices, so they anti-commute. So this combination is 0. And sigma 1 sigma 2 is I sigma 3. So this is I sigma 3, and therefore we've gotten back the Hamiltonian that we started with. Okay, so this is all straightforward. If you want some practice with this, I invite you to verify the rest of the algebra. We haven't quite finished, though, because I told you that there should be some Z2 symmetry, which is fermion number. And so what is that going to be? Well, in this problem, minus 1 to the f, we can take it to be equal to the matrix sigma 3, which is this matrix. So the top component of the wave function will be bosonic, and the bottom component will be fermionic, according to this definition. Okay, good. So here's an example with supersymmetry. But what is supersymmetry good for? So next, what I'll do is I'll tell you some of the most elementary basic consequences of this algebra. They're true in quantum mechanics, and they'll also be true in quantum field theory. And then we'll see how they work out in this example that we've set up. Okay. So going back to this algebra, I emphasized before, but it's important, so let me say it again. The first thing just says that Q is a symmetry, and the second thing is really the non-trivial part. This is an algebra that involves the Hamiltonian non-trivially. And so what that means is that supersymmetry will actually constrain the energy levels in our problem. It will constrain the properties of the Hamiltonian. So let me tell you some general consequences. They won't depend on the number of supercharges that we have. So we'll just do the most elementary consequences. So the first is that all energies E are positive. We saw a hint of that in this example because we got a positive definite potential energy, but we don't know really where it came from. Let's see how to prove this. So suppose you have some state psi, and H psi is E psi. So then we can consider the following. So we take this, which is some positive number, the norm, times E, and we can write it as psi. Now we use the fact that H is equal to Q squared. So I'll suppress the indices since I'm just talking about one state, one supercharge. And now I use the fact that Q dagger is Q. So this is in fact the norm of Q psi, which is of course greater than or equal to 0. Okay, so that's a basic consequence of supersymmetry. In any supersymmetric theory, the energies are positive definite. Now, there's a nice corollary of this. Suppose we want to minimize the energy. Well, we have an inequality. So the states of minimum energy are those that saturate that inequality. So E equals 0 states are necessarily ground states. We can say more about them if we look at the details of this argument here. So suppose E is equal to 0, then the left-hand side of this equation is 0. Therefore, so is the right-hand side. So a ground state, so these kind of states satisfy Qi on psi is 0 for all I. So any energy equals 0 ground state is automatically annihilated by all of the supercharges. This turns out to be an extremely powerful observation. Why is it so? Well, if you go back and look at Qi squared is equal to H, in quantum mechanics and generally in field theory, H is usually a second order operator. So if you're trying to find energy eigenstates, you need to look at some second order differential equation. But Q is a square root of H. So Q is going to be a first order differential operator. And you see that here. And so finding states of exact energy 0 will boil down to solving a first order differential equation. So that's a major simplification. Now, in general, when you have a symmetry, you say that it is preserved if the generators annihilate the vacuum. Now, in this problem, we see that supersymmetry is preserved that is, the supercharges annihilate a ground state if and only if the ground state has zero energy. So you could wonder why I'm talking about this. We're just doing quantum mechanics. Usually when you're doing quantum mechanics, you don't think that symmetries can be spontaneously broken. If there are symmetries of the Hamiltonian, there's symmetries of the true vacuum. But that actually turns out to not be the case for supersymmetry. So supersymmetry can be broken even in quantum mechanics. And we're going to see an example in this model very soon. Okay. Yes?
Isn't it really just a matter of terminology? And then
Isn't it a terminology?
you say that supersymmetry can be broken in quantum mechanics, while ordinary symmetries cannot be broken in quantum mechanics. But it seems like it's more a matter of terminology.
No, I don't think it's a matter of terminology. I mean, if you consider, for instance, a double well potential in quantum mechanics, which is Z2 symmetric. It's an interesting fact that the true ground state is actually Z2 symmetric, even though and there are very general theorems about that, right? And those, maybe there are exceptions to them that are tricky and somehow evade the general theorems, but in supersymmetry, we'll see that supersymmetry breaking spontaneously will be kind of generic. Yeah. Unitary theories. Yes. Throughout, I am assuming that the Hamiltonian is Hermitian, which follows from this. Okay, so another fundamental consequence of the algebra is, so we've looked at E equals 0 states a little bit. Let's now look at E greater than 0 states. And these are always degenerate. Let's see this in more detail. So let's consider B to be any bosonic state, which is an energy eigenstate. So HB is EB, and for simplicity, I'll take B to be normalized. So BB is 1. And here I'm assuming that E is positive. So we'll define another state, a friend of this bosonic state, by F is defined as 1 over root E Q B. Now you can check that H on F. So first of all, I divided by E here. So that's where I assumed that E was positive. This is to make F normalized. So right, if I compute the norm of F, I'll get a Q squared term, which is the Hamiltonian. I'll get an E, and that will cancel. You can also verify that H on this fermionic state is also has the same eigenvalue. So this is what I meant by saying that positive energy states are degenerate. They always come in these Bose-Fermi pairs. And here I've used only one supercharge. If we had more supercharges, this implies more degeneracy. Okay, so I'd now like to verify for you these very general properties of the algebra in the context of this simple example that is hopefully still on the board. Here, this particle with spin. So how will we do it? This looks like a pretty complicated interacting thing. W could be some degree 10 polynomial, and then we'd have some degree 18 potential there. How would we even get started? So to proceed, we'll first do semi-classical quantization. So I'll imagine that the potential is very steep, so the particle only fluctuates a little bit near the minima of the potential. And we'll try and verify the spectrum, the spectrum that we find using semi-classical quantization enjoys all the properties that we've discussed above. Okay. So what do I want to do here? So we want to take so where are the minima of this potential? So the minima are at W prime equals 0. So these are critical points of W. And so near a critical point, I will expand W prime of x is equal to, so near the ith critical point, so xi is a critical point. And for simplicity, I'll assume that these numbers that I get here, these omega I, are all non-zero. So I'll assume that W is non-degenerate. And maybe let me also say that I'll assume that W prime squared grows at infinity. So we have a nice bounded potential. Okay. So this is going to be our approximation. We'll look near x is xi, one of the minima, and we'll plug in here this formula for W prime. And notice that since we're proceeding semi-classically, to leading order I can neglect the spin coupling. So I can neglect that term, which goes like h bar because it involves the spin. Okay, so then the Hamiltonian looks like plus terms of order h bar. Okay, so it's just a harmonic oscillator. But since we have a particle with spin, we actually have two harmonic oscillators. And to this order, they're not even talking to each other. There's nothing that involves the spin at all. Okay, so that means we all know how to quantize the harmonic oscillator. So that means we're going to end up with two candidate ground states located near each critical point. So the first I'll call BI is a bosonic ground state. And what does its wave function look like? Well, so it's bosonic, so it's got a 0 down here. And then it goes like e to the minus m over 2 m omega I. We need an absolute value of omega I. This will be actually important. So here, omega I could have either sign, whereas here it appears squared. So when we take the square root, we introduce an absolute value. Okay, so here's the bosonic thing, the bosonic candidate ground state. And there's also a friend, which is a candidate fermionic ground state. 0, and then the same thing here. Okay, so is this clear? Just by doing semi-classical analysis, we end up with two harmonic oscillators near each critical point, and so we get a bosonic candidate ground state and a fermionic candidate ground state. Sorry? Yeah, the W double prime term is order h bar, so it can be dropped. to leading order. We'll soon see that it's important, but to... What is the dimensionless parameter? Sorry.
I think you're in trouble, but it's going to come back anyway, so you don't have to answer these questions.
Well, no, I mean, I think in order to find you could have asked whether I needed to take into account the W double prime term to determine the candidate ground states in the way that I'm proceeding. And I think that you don't, because it is order h bar. Now you ask, what's the dimensionless parameter?
In the simple harmonic oscillator limited, it's like h bar omega, which is the same order of all the other things, but it's also just a constant shift.
Well, I'm about to yeah, I'm about to do the constant.
But it's, yeah.
No, if I want to compute the energy, I haven't told you what the energies of these are. I've just said the word candidate ground state. So all I did was I minimized this term.
Sorry, I apologize. You didn't say which one was lower energy.
No. Okay, so as is being pointed out by the crowd, I have succeeded in minimizing this term, but I didn't look at minimizing this term. Now, in this semi-classical expansion, when we take another derivative, this just becomes a constant shift. And so all we need to do is compute what is the energy of each of these states. So let's do that. Let's consider H acting on this candidate, this bosonic state Bi that I cooked up. So we get a half h bar absolute value omega I. That's from the harmonic oscillator part. And then now we come in here and take this part into account. See, now the ground state energy is of order h bar, so we need to pay attention to this. Then we get minus a half h bar omega I. Notice that one has the absolute value and the other does not. Okay, so similarly we find this for the energy in this approximation for this fermionic state that I introduced here. And so now we see which is the true ground state depends, which is lower energy, depends on the sign of omega. So if omega is greater than 0, then this cancels and this adds. And so the boson Bi is the ground state. And if it's less than 0, the fermion is the ground state. Now we can reformulate this. So notice that these omegas are second derivatives of the superpotential. So the boson is the ground state if xi is a minima, and the fermion is a ground state if xi is a local maxima. Okay. So what have we succeeded in doing? So we found in this semi-classical quantization that around every critical point of the potential, every 0 of the potential, there is exactly one ground state, and that ground state is supersymmetric and has exactly 0 energy. Yes?
Well, it looks like the the second term, this W double prime term, shifts the energy of the ground state pretty significantly because they're actually, the contribution from both terms are of the same order. So I'm wondering if that term, if you include it in the beginning, does it change the...
No, so, no, maybe I should have said it this way. If you do this expansion, then W double prime is a constant. So this Hamiltonian is a sum of two Hamiltonians that commute. So finding their energy eigenstates, you just find the energy levels of each and add them up. Okay, so that was, so we verified some of the expected properties in this semi-classical approximation. We can, of course, also look at the excited states. So let's look at the excited states. So again, keeping in this harmonic oscillator approximation, so we know what the energies are. So let's introduce bosonic states, B, N, I, with n greater than or equal to 0, the occupation number, and n equals 0, the state that we just talked about there. And we can also similarly introduce fermionic states. Now, what are their energies? So E, B, N will be equal to h bar absolute value omega I times n plus a half minus h bar over 2 omega I, and E, F, N. So again, I'm just adding up the two contributions, one from the kinetic plus potential term and the other from the spin part. Okay. So we're expecting to find degeneracy on the excited state. So let's look at the case omega I greater than 0. So we know that the bosonic state with n equals 0 sits as the lone ground state. And what you can see if you compare these formulas is that there is degeneracy between B n plus 1 and F n, for n greater than or equal to 0. So this was the expected degeneracy. So I told you that a general consequence of the supersymmetry algebra is that excited states come in Bose-Fermi pairs. And here they are in this case. Okay, is this clear? Okay, good. So now I would like to teach you another general tool applicable in all supersymmetric theories, and then again apply it to this example. Okay, so what is this general tool? The general tool is called the index, the Witten index. So now we'll divorce ourselves again from this example for a minute. We'll talk about something general, and then we'll go back and see it in the context of this example. So let's let n b e be equal to the number of bosonic ground states, bosonic states of energy E. More precisely, I mean look at an energy level and compute the dimension of that eigenspace. And we can define a similar thing for the fermionic states. So here in this discussion, since I want to make sure these are actual numbers, I'm going to assume that the spectrum is discrete. Otherwise, I wouldn't be able to make sense of these as actual numbers. Now let's consider the difference. NBE minus NFE. There are two basic cases. So let's first assume that E is greater than 0. So if E is greater than 0, then we know that if the energy level is occupied, the bosonic and fermionic states come in equal numbers related by the supercharge. So therefore, this is 0 if E is positive. On the other hand, if we look at the sector of 0 energy, then that is the ground states, the candidate supersymmetric ground states, then all of those states are annihilated by all the supercharges, and so supersymmetry tells us nothing. So this could be any integer. Okay, this integer is called the Witten index. So let's see how to write it. So we've seen how to write it in terms of the 0 energy states. Let me write it in another way. Okay, on the one hand, we just defined it to be NBE equals 0 minus NF E equals 0. Now, it's important that we can rewrite this as a trace. So we'll rewrite it as trace minus 1 to the f e to the minus beta h. Why is this formula correct? Well, for states of positive energy, we get e to the minus beta e. This minus 1 to the f means we take the difference as we did above, and we just get 0. So the positive energy states don't contribute. And for the negative energy state, for the 0 energy states, it's clearly just this. Okay. So this fundamental quantity has some important properties, which I'd like to tell you about, and then we're going to go see them. So first of all, the index is independent of beta. That's clear from the way I defined it. It's just this number, which doesn't depend on beta. Well, what was the role of beta in this discussion? Then the role of beta is to make this this sum well defined. So I could have tried to define trace minus 1 to the f without e to the minus beta h. Then I'd have a sum of plus and minus signs over an infinite dimensional space, and that would not be well defined. So I introduced this factor e to the minus beta h to regulate the sum. That's actually a very powerful idea, because when beta goes to 0, so it's independent of beta, so you could try to compute it using any limit you like. And when beta goes to 0, your quantum mechanics problem will become weakly coupled. So this is useful for looking at the beta to 0 limit. You can compute there and then get the energy, the difference between the number of bosonic and fermionic ground states that way. Let's go over here. Let's go back over here. Okay. The next important thing is that the index can be reliably computed using approximate techniques. So more specifically, we can use any approximation that preserves supersymmetry. Why is this the case? So when you do an approximate calculation, you might make a mistake if you're computing the number of zero energy states. There might be that some of the states that you think are zero energy actually have some small positive energy. But if they do have some true small positive energy, then they have to come in Bose-Fermi pairs. And those Bose-Fermi pairs will cancel when you compute the index. Finally, the index does not change under small deformations. And I'll try and say what this means. Of coupling constants. What does that mean? So imagine you have some potential. Here's some potential. What does it mean to do a small deformation? So for this purpose, small deformation will mean anything under which the energy eigenvalues evolve analytically if we do that deformation. So for instance, we can fix the asymptotics of this potential and wiggle the interior. So we could change this shape to be that. So this counts as a small deformation. So the energy spectrum may change radically, but importantly, as you dial continuously from this potential to this potential, the energy eigenvalues evolve analytically. Now, of course, the true number of ground states may change. When you do that, we haven't learned what the true number of ground states is, but if they do change, then they change in Bose-Fermi pairs. They move off of E equals 0 into a generic E greater than 0 representation of supersymmetry where they must become degenerate. Okay. So this Witten index is very useful. So one of the major reasons why it's useful is that the fact that you can compute it using any approximation technique and the fact that the index doesn't change under small deformations means that it's very computable. So it's always great when you have some quantity that you can really get your hands on and compute. And that's a kind of hint of many of the results in supersymmetric localization that will come next week. I should also mention that the Witten index is a kind of diagnostic test for supersymmetry breaking. If the Witten index is non-zero, then it means that there is at least one energy zero state. Which means that supersymmetry is unbroken. What about if the index equals 0? If the index equals 0, then we don't know. There could be no energy zero states, or they could have canceled out in the sum. So for this reason, it's because the Witten index is computable, it's often easy to prove, to evaluate it, find a non-zero answer, and prove that supersymmetry is unbroken, even at the quantum level. Okay. Are there questions about these general properties of the index? let's go back to our little example and try and understand the index.
Comment about Gaussian condensation, because in the case of Gaussian condensation,
Gaugino condensation.
yeah,
You're like 10 lectures ahead of me.
you've got no zero index, but you know that the SUSY is dynamically broken. So
I think this question will not be understandable to most people. Do you have a question about the definition of the index? Or its proper, I mean, okay.
Can I ask a question?
Yeah.
So, I mean, if the index is 0, all you know is the number of bosonic and fermionic ground states, right?
Yeah, but could be 0.
Right. I see. That's fine. But is there a way to write down, for example, if you know one of the ground states, is there a way to write down the corresponding fermionic ground state? That's the pair of the bosonic one?
No, so crucially, the E equals 0. So the question was, the question was, can I write down the paired bosonic and fermionic ground states? And crucially, the E equals 0 states are not paired. If the E equals 0 states had been paired, under supersymmetry, the index would have always been 0. Right? So there are these two different basic fundamental representations of supersymmetry. There are the energy 0 states, which are annihilated by all the superchargers, and then supersymmetry tells us nothing because Q acts trivially on them. Then there are the excited states of positive energy, and those are related to each other. They come in degenerate pairs under supersymmetry.
I see.
More questions? None. Okay. Good. So let's go back to our example and try and understand the Witten index given this semi-classical approximation. So I emphasized that we could compute the Witten index in any approximation scheme. And so we were here studying this problem in some approximation scheme. So let's evaluate the index. Okay, so it was by definition the difference between the number of bosonic and fermionic ground states. So here, when did we have a bosonic ground state? We had a bosonic ground state Bi whenever we had a minima of W. And we had a fermionic one whenever we had a maxima of W. So this is equal to the number of minima minus the number of maxima. So let's look at this for some candidate W's. So for instance, we can consider a very simple W of x, which looks like this. So just some kind of upward sloping function with one minima. So then I'll call this I. Then I is equal to 1 because we have one minima. So in this model, supersymmetry is unbroken. Whatever the true ground state is, we don't know where it is, but there is one ground state, at least one ground state of energy E equals 0. Another candidate W, give it the same asymptotics, but have it wiggle in the middle. Okay, so we know from the general discussion that we can interpolate between these two by a small deformation. I fix the asymptotics and smoothly deform the potential in the middle, smoothly deform the superpotential in the middle, and the energy eigenvalues will evolve continuously. And so the index must be the same. And now you can try and verify that using this formula. So here we have 1, 2, 3 minima and 1, 2 maxima. How can we get an example where the index is 0? Well, One way to do that is to take a function that has no critical points. So let's imagine w of x looks like this. So there are no critical points. So the associated potential, if I make this very big, if I make the derivatives very big, will be just some positive function. So let me now put the origin. So v is w prime of x squared. There are no zeros of this function, so whatever it is, it's up above the origin. And if I make w prime very big, then it's clear that supersymmetry is being broken classically very badly, because we're very far from being able to have a zero energy state, because the potential is very far above zero. Okay? So here, it's clear that the index is 0, because there are no critical points. So there are no minima and no maxima of w. Of course, we could have also considered a situation with the same asymptotics, something like that. Okay, now there are a bunch of critical points. So now the potential has a bunch of zeros, and there are a bunch of candidate ground states. But we can compute the index. The number of minima is 2, and the number of maxima is also 2. So we see the deformation invariance of the index working in front of our eyes. So we know that we can interpolate between this function and this function by fixing the asymptotics, and therefore the energy spectrum will evolve continuously. Therefore the indices must agree. Any questions about this? Okay, let's keep going then. Now, another general feature that we discussed is that the supersymmetry algebra, the fact that Q is a square root of the Hamiltonian, sometimes makes it easier to find states that are in fact annihilated by the supercharges. States that are annihilated by the supercharges in this context are the exact energy eigenstates. So that's asking for the exact wave function of the ground state. And what we'll be able to see is that we can do that sometimes in this problem. Okay, so let's find the exact ground states. So we're done with this approximation. We're going to try and find the exact ground states, provided they have E equals 0, of course. If there are states, if the true ground state has positive energy, it won't be annihilated by the supercharges, and we won't be able to use these techniques. Okay, so what do? Well, we simply take our supercharge Qi, and we operate it on a wave function, and we demand that we get 0. Okay? Now, I just erased the definition of Qi, but it's just some combination of sigma 3 and derivative operators and things like that. So it's pretty easy to work out what this means on the individual components. So what does it mean? It means that d phi plus minus dx equals minus plus m over h bar phi plus minus of x times w prime. So that's what this equation means. As promised, this equation is first order. So I emphasize that since Q is a square root of the Hamiltonian, saying Q equals 0 means you have a first order differential equation. Second order differential equations are hard, but first order differential equations are easy. Let's integrate this. So we end up, by integrating this, we end up with a two-dimensional space. What's that space? So here a and b are just some constants of integration. Okay, so we've solved this equation. Does that mean that we have two energy eigenstates? The answer is no, because we have to be cautious about the norm here. So how can we tell whether these states are normalizable?
Are you taking W to be 0 somewhere while integrating it?
No.
Could you repeat the question?
The question was, am I taking W to be 0? And I said the answer was no, but I don't...
No, at a particular point, because like while integrating, you have an integration constant. Oh, they're embedded in. Okay.
Good. So how do we tell if they're normalizable? Well, we could look at this state. So in order to see if this state is normalizable, we'd take the square of this and try and integrate it. And so it would be normalizable if W grows at infinity, at both positive infinity and negative infinity. But if that were the case, then this one would be non-normalizable. So if W of plus and minus infinity is plus and minus infinity, then A state normalizable, B not. If it's the opposite, suppose it's the opposite. Suppose at infinity, W goes to negative infinity, and at minus infinity, it goes to, sorry, it should have been no minus sign there. Then the B state is normalizable. A naught. Okay. Finally, we can consider the case where W goes to plus infinity at plus infinity and minus infinity at minus infinity. And then you can see that you're going to have a problem on both sides. So I guess I need a new board. Okay, so if W of infinity is, say, positive and W of minus infinity is negative, then if we look at, say, this state, we find a problem at plus infinity, and at this state, we find a problem at minus infinity. So neither is normalizable. And same with the opposite case. Okay, so we have now succeeded in determining the exact ground state in the special case when it is supersymmetric. So we can now examine some features of that answer. So let's look at this case. W of plus infinity is plus infinity, and W of minus infinity is minus infinity. Sorry, W of minus infinity is plus infinity. That's the situation here. So W is growing on both sides. And we found that the index here was 1 by our approximate calculation. On the other hand, we have now determined that there is exactly one ground state in this problem, and that it is bosonic because it has a component here and not here. So from the exact answer, we also find index 1. That's, of course, expected. The index is supposed to be insensitive to whether we use the exact spectrum or a supersymmetric approximation. We can also look at these cases here, where the limits were different, and we find no true E equals 0 state. So there is some ground state of this problem, but it's not supersymmetric. That's the situation over here. And here we find I equals 0, as expected. So you see the Witten index working in practice. Yeah.
So given all the information that we were able to get about the BPS states, can we say something about non-BPS states?
Well, that's hard. I mean,
Can you repeat the question?
the question was, what can I say about non-BPS states? What can I say about non-BPS states? So I emphasized that we could do a lot. Sorry, first of all, the terminology BPS means annihilated by some of the Q's. In this case, all of the Q's. So I don't know of any good general answer to that. What can I say about the E equals 0 states? But let me say that in later lectures, we'll maybe see that in field theory, there's sometimes an interesting answer where there are vacuum states annihilated by all the supercharges, and then there are excited states annihilated by some fraction of the supercharges. And then there are sort of completely excited states which are not annihilated by any supercharges. And so in that case, you can still say something about some excited states. But here, I don't think supersymmetry helps you that much with the excited states.
Can you say something like scattering states?
Well, the question was, what can I say about scattering states? So I mean, I've considered this potential to be bounded, so that I can, so that it's simpler. You can, of course, consider supersymmetric quantum mechanics where the potential fall off is slower, and then you'll find a continuum of states, and then investigating the index in those cases is much more subtle, but can be done. There you find, for instance, that it is not truly independent of beta, at least in a naive definition, the way I've defined it. Yes?
Could you comment on the example you have there where it seems like you have possible minimums, but it seems to go twice infinity out to minus x?
So this one here. Right, so here, semi-classically, we found a whole bunch, 4, I guess, candidate ground states. And quantum mechanically, there are no energy 0 states. Of course, there is some ground state of this system. It just doesn't have energy equal to 0. So what it means is that if you look at these semi-classical states, their energies are all slightly lifted by tunneling. So maybe as a general comment, I didn't mention the approximation that we worked in, where we found the approximate energy 0 states located at each of the critical points. That approximation is good to all orders in perturbation theory. So these E equals 0 states, at least the approximate ground states that we found there, are not going to be lifted at any order in perturbation theory, but they can be lifted by tunneling, and that's been studied in great detail.
How do one detect this in terms of the Hamiltonian itself?
How would I detect? The question was, how would I detect the lifting in terms of the Hamiltonian?
Yeah.
So you would have to compute the tunneling. You can do that. So we have a problem now where we have 4 candidate states, and we could try and compute their overlaps by looking for tunneling solutions. And you can do that in the context of this problem, and it has been done. More questions? Okay, so just to emphasize this fact that you can write the exact ground state, at least in some cases, is pretty non-trivial. W can be quite a complicated function, and so the problem looks very complicated if you just looked at the Hamiltonian, but nevertheless you get an exact formula for the wave function of the ground state. Let me just plot one so you see what it looks like. So let's take W to be something that's kind of quartic. Make this deeper. But not symmetric. So here's W. So that means there were 3 candidate states at the critical points. So W is quartic. That means the potential V of x would be sextic. So it looks like that. These are supposed to be exactly at 0. So there is candidate ground state sort of localized in each bump here. So there's one here, and one here. On the other hand, we're in the situation where this is the exact true ground state, and so we can make a plot of that wave function. So what does it look like? So it goes something like this. So here, this peak is here, and this peak is approximately here, and it's got some support in the middle, but it's not really peaked there. And so you could think that what happened is that the true ground state is some kind of combination of this and this. This state has been lifted, and the antisymmetric combination of this and this has also been lifted by tunneling effects. So this is what you get just by plugging into these formulas.
Would those lifted states be the partners?
Yes, they go, well, at least infinitesimally they go off, yeah, together. More questions? Okay, so we're almost to the end of where I wanted to get. There's one final thing I want to say in the context of this model, which is that doesn't really seem to have much to do with fermions. And you might have thought that supersymmetry should be all about bosons and fermions. So I'd like to try and make that more manifest in this model that we had. So let's recall that H was p squared over 2m plus m over 2 w prime squared minus h bar sigma 3 over 2 times w double prime. Now, how will I make fermions manifest? Well, you see, when you have we have here a particle with spin. So the spin is some two-dimensional Hilbert space. And what I'd like to do is just rewrite that Hilbert space in terms of fermionic degrees of freedom. So let's introduce fermions psi, which obey the following canonical commutation relations, anti-commutation relations. So it'll be complex psi. It has a partner psi bar. And the non-trivial one is that you get some h bar over m there, some non-zero answer. Okay, so quantization of these commutation relations leads to a two-dimensional space. So we can view our particle with spin as having this two-dimensional space of states tensor with functions of x. That's the Hilbert space. So how will we proceed? So to realize this in our model, what we do is we write psi is this, and psi bar is this, where sigma plus and sigma minus is sigma 1 plus I sigma 2, and sigma minus, maybe I need a half, is sigma 1 minus I sigma 2. So this matrix, if you're unfamiliar, is the matrix 0, 1, 0, 0. Acting on this two-dimensional space of states. So now we can remove, we can rewrite all the spin parts of the Hamiltonian in terms of the operators psi and psi bar. So how do we do that? Well, we can write H is p squared over 2m. So these parts just come for the ride. They depended only on the x variable. And now we can write m over 2 commutator of psi psi bar w double prime of x. So this Hamiltonian with those canonical anti-commutation relations is the same as our initial problem. But now, minus 1 to the f just counts psi's and psi bars. Okay, so finally let me say that you can get this by quantizing a Lagrangian. That looks like this. So this is a classical Lagrangian now, where psi and psi bar are anti-commuting completely. So this non-trivial anti-commutator arises by canonical quantization, and here in this classical Lagrangian, psi and psi bar just anti-commute. Okay, so let me stop here. The next time we talk, we'll see how to produce supersymmetric Lagrangians en masse, and we'll sort of demystify where this structure here came from. So why was the potential energy related to the magnetic field? We'll see how to get that from first principles. Okay, I'll stop here. Thank you.